Hi everyone, my name is Young Lee. I'm a senior data scientist at Sophos AI. In this talk, I will present how to create new spam samples and how to catching them with a text generating AI model. Let me start with simple questions. The first one is we have two spam messages here. Which one is spam? The first one, Santa calling and blah, blah, and call the number to book your time. Yeah, the first one is obvious spam message. How about the next one? A lot of the sickness and take it easy, hope you feel better. Yeah, obviously it's not the spam. And the next one, which one is spam? The first one, Santa calling and something about the premium service. And yeah, it's highly likely another spam. And how about the next one? Santa calling and something about the photo and the cat. So probably it's another spam message. So we can say the first one is highly likely and the second one is less likely spam. Okay, let's move on to the final quiz. So which one is AI generated spam message? Can you guess? The first one and the second one also has the same first 5 words, but you can see these are different. So actually both of them are generated by our AI model. We will talk about how we can generate these spam messages. What is spam? Spam messages are irrelevant or unsolicited messages sent over the internet to a large number of users. Their main purpose are advertising or phishing or spreading malware software. In spam ecosystem, there are many different the players, but we are a detective today. We have a small training data set. In our case, which we have only a few hundred messages. That's our evidence. And our goal is to build a strong machine learning model for spam detection. Also, we wanted to generate new spam messages to augment the small data set. So finally, we are going to improve our model's performance with the generated data set. And the first step is we are going to train a spam detection model. There are several ways to achieve that. The simple approach is signature-based one. The spam message here, we can add some text, for example, Santa calling and the call number as block list. And also another way is we can add the sender's number, for example, sender's ID as block list. This way we can detect the exact same one. However, this method is not scalable. Also, it will not detect new ones. So the next approach will be a machine learning based one. Many machine learning models need to convert the raw text into a numerical format, and often term frequency IDF is most successful choice for machine learning features. The TF-IDF can tell us how important a word to a document. For example, Santa and calling, we can assign a specific number for the text. We trained the two ML models with these features. Naive Bayesian and the random forest are the models trained with these features. And then also we can utilize the modern deep neural network approaches. These new approaches can use the raw text as it is, so we can consider the text as a sequence of orders. So Santa calling, these are the input to the features, input to the models. And for example, LSTM, long short-term memory can run the temporal relations between tokens. And also we can use convolutional neural network. Often CNN models was trained to recognize images, but also we can consider the text as a sequence of one-dimensional data. And also we can use the same mechanism from the CNN. Finally, we can train a transformer-based natural language processing models. These models are so powerful and they can run complicated attentional weight between tokens. And GPT and BERT are the most successful state-of-art of NLP models based on the transformer architecture. This table summarizes the previous approaches and shows pros and cons. The simple signature-based one, we only require small data for right signatures. However, their detection coverage is quite limited because this method only can detect exact matching ones. Also, the signatures need to be frequently rewritten to detect new ones. And the second, simple ML models requires a large size data set. Also, this method can detect not just exact, but similar ones can be detected with this method. However, retraining is frequently required to detect the new ones. And finally, pre-trained natural language models, for example, GPT-2, only requires small data for fine-tuning, and it can detect similar as well as unseen samples. So this method also required pre-training, but pre-training is required less frequently compared to other methods. We use GPT-2 as our text generating AI model. The GPT-2 is one of the state-of-art natural language processing models from OpenAI. It is generative, which means the model can generate coherent text from a short input text. Also, it is a pre-trained model. The model was pre-trained to predict the next word from a large-scale data set. The data set was collected from Wikipedia or many different websites, also many different books. And the model used modern transformer-based architecture. This architecture runs additional attentional weight between tokens. This training process allows the model to generate a long, coherent text. The GPT has 3 different versions. The first GPT-1 was released in 2018. And then next year, the next version, GPT-2, was released. But the next version, 2 version, has 10 times larger parameter size. And then GPT-3 is the latest version, was released in 2020, but the model size was huge. So actually the model cannot be loaded into a single machine, but we can access the GPT-3 from the Microsoft Cloud APIs. That's why we are going to use GPT-2 for our work. Also, the GPT-2 has many different sizes. For example, GPT-2 Small has 12 transformer blocks, and the largest one, Extra Large, has 48 transformer blocks in it. However, we choose to use the smallest one called Distilled GPT-2, which has only 6 transformer blocks. However, we obtained a very impressive result in our experiments. The next diagram shows GPT's internal architecture. GPT-2 has been trained to predict the next word. For example, here, the input text is a robot must obey the orders given. That's the input. And the model was trained to predict the next word. The next word is it. So this way, GPT-2 can have ability to generate a long and coherent text. How we can convert the text generating AI model to a classification model. GPT-2 has many different headers. For natural language processing task, they use a language header, which has a number, the number of vocabulary size as the output. So usually the English model has about 30,000 outputs as final layer. For example, here, the final layer will generate it as a 70%. So we can take it as a final output for this language header. For our classification problem, we can remove the language header and we can insert a different header, classification header, which will have two outputs because we will have whether the input text is spam or ham. For example, if the output spam is 95%, then we can take the text as the ham message. This way we can train the model as classification model, also text generation model. For our experiment, we use a small data set, SMS spam data set from UCI ML repository. The repository has about 5,000 SMS samples, but we divided the samples into 3 different subsets. The first set is trained 200. This one has only 200 samples. And then we have 1,000 training set, which has 1,000 training data set. And we use the remaining samples as our test data set. For experiment, we trained 5 different ML models. For neural network models, we have GPT and CNN LSTM models. Also, we have 2 conventional models, which include random forest and naive Bayesian models. This diagram compares our GPT-2 model with other 4 baseline models. The ROC curve shows the x-axis as false positive rate and the y-axis as true positive rate. The figure A shows the result when we trained the models with only 200 samples. The top one, blue one, is the GPT's ROC curve, and the bottom green one is LSTM's ROC curve. As you can see, GPT-2 outperformed all baseline models significantly. Specifically, the GPT model achieved 90% true positive rate at false positive 1 in 100. The figure B shows the performance when we trained all models with 100 samples. As you can see, we can see significant performance improvement with the large data set size. However, we can see that still the GPT achieved the best and consistent result in both cases. Also, interestingly, the LSTM model does not work with small 200 samples, but we can see significant performance improvement with the 100 sample size. From the previous experience, we noticed that the size of a training data set matters. As we can have more data, we can improve the performance. Specifically, deep neural networks are hungry for a large data set. Training deep neural network, however, with the small data does not always guarantee better result. As you can see, the LSTM was outperformed by conventional models when the training data set is quite small. Also, we noticed that the pre-trained model and then fine-tuning the model with a small data outperformed the baseline models. So GPT-2 is a quite strong model for our experiment. We know that the data size is important. However, the cost of data labeling is very expensive. Your data science and the engineering team are not cheap at all. If you want to do the data labeling manually, probably 80% of your valuable time will be spent in data cleaning and manual labeling. Also, you can't guarantee the data quality even with the manual work. So copies in, copies out, a model is as good as the data used to build the model. Alternatively, we can use crowdsourcing or outsourcing to the data labeling. However, this method also expensive as approach. So high quality data augmentation is key to success any ML project. The next section is how to generate new spams. There are several ways to enlarge your training data set. There are simple approaches. For example, we can replace words with synonyms. Also, we can insert or remove random words in text data. However, this method has limitations to generate a variety of high quality samples. Often the synonym in one sentence does not work in another sentence. Another approach is to utilize modern generative language models. For example, GPT can generate long coherent text data. However, we don't have the control to the style or contents of the GPT's output. To tackle those technical problems, researchers introduced controlled text generation methods. PPLM, plug and play language model, is one of them. This approach trained to learn a classification model which can control the style or contents of the output. And then we can update the final output with this model. So our implementation is based on the PPLM approach. And there's another one called control. This approach trained to condition on a control code that can govern the style of contents. For example, the control, we can use already specific topic words. For example, to generate the sports-related text, we can always use some sports-related words. This figure shows the PPLM's high-level overview. PPLM used GPT-2 as its internal text-generating AI model, but it also trained a small attribute model. The attribute model can drive the direction of text-generating power to the desired direction. For example, we can apply the attribute model to predict the input is text, input is spam or not, then we can change the direction to generate the desired the spam message. PPLM has 3 steps in training. This diagram shows each step. For example, here, the input data is the chicken taste, and we are going to generate the next word. In step 1, the pod path will learn the original GPT-2, and the output is okay in this case. So the chicken tastes okay. However, our attribute model can give us signal whether the input is really positive or not, because the model has been trained to give us whether the input is positive or not. However, okay, it's not that positive, so we can change the direction slightly towards to delicious. So finally, we can get the delicious as our final output. So the final text will be the chicken taste delicious instead of okay. Also, we can see the same the direction from the optimization steps. For example, the chicken taste, the black dot is the current point, and we are going to move the direction toward to improve the probability of the attribute model as well as the language model. So actually we move to the right and up. So we will get the delicious as a final output instead of okay. for spam generation task, we use the same SMS spam data. We have 200 training data set, and we use the same 3,000 samples as our test data. We are going to generate 1,000 samples out of 200. So our approach is to generate 5 samples from each training sample. But we also needed to use some of the tokens as input to generate relevant text. So we used the first 5 words as input text, and then also we assigned the same label as input to the attribute model. For example, we generated spam data from the spam. Also, we generate ham from the original ham messages. Let's have a look at some of the examples generated by the PPLM model. This one, we generate spam samples from the original spam. The original spam is the top one, and each one has the first 5 words are same. Santa calling was little one. And as you can see, spam 1, you can see some the premium service related one. Yeah, this one is obviously spam message, and also the second one. So it's about another payment service. So the model generated new spam message out of the original one. Next, we will see whether we can generate ham samples from the same spam. To generate ham 1, let's have a look at that. Center calling, but this case, there's nothing about advertisement, but some interesting text. And spam 2 also, it's about the portal and the cat. So we can say it's not absolute spam, but less likely, spam. Yeah, we can consider this another ham message from the original one. Also, we can analyze our GPT model's internal representation using a LIME analysis. LIME is a local interpret model agnostic explanation method, which can tell us which tokens are high weighted in the internal GPT representation. For example, the A generated spam message. The text in orange shows suspicious tokens, and the text in blue is non-suspicious tokens. The figure A shows the high-weighted tokens, for example, premium, online, monthly members are something about the premium service. And the second one, generated ham, we don't see any high-weighted orange tokens here. Okay, let's have a look at some of the different samples, ham samples from the ham. So from the original ham message, we generated 2 new ham samples here. The ham one, it's about eating avocado, and the second one is about eating vegetable. So we can say it's not spam, but something interesting topic about the sickness. And then we will see whether we can turn the original ham into spam messages. The spam one has about the phone data service. It's something about advertisement, we can say that. Also, the spam 2 is going to about introduce some service related thing here. So our model can generate ham from ham, also generate spam from ham as well. Let's have a look at the LIME analysis for the new samples. The first one, generate ham, spam actually. We can see phone service on weekly. Yeah, those ones are high weighted. So we can say that's a spam. And the next one, generate ham we don't see any high-weighted orange tokens here. The next step is how we can improve our model's classification performance. Again, we use the same data set, SMS spam data set. Our original data set has 200 samples, which include about 175 ham and 25 spam samples. And then we generate 1,000 samples out of 200. And then we use the same 3,000 test data set. We can use all samples, but it is better to assign a different sample weight, because our original sample has high quality, as the generated samples maybe will not have the same quality. So we assigned a 2 times high weight for the original samples for our training. With the new samples and the different sample weight, we trained 3 models. And this hour's curves compares the performance. The bottom green one is the original model, only trained with 200 samples. And then the second orange one, we trained the model with the original 1,000 samples. And then finally, the green one is the model trained with 200 plus augmented 1,000 samples. As you can see, we achieved comparable performance with the PPLM approach, which the model only can be achieved with the real 1,000 samples. In summary, still the size of training data is important. Also, we noticed that pre-trained models outperformed the baseline models with small data. And high quality data augmentation matters. The synthetic samples were as good as using very expensive hand-labeled samples. In conclusion, GPT, a text-generated AI model, can be trained to detect spam. Also, it can be retrained to generate new spam samples and augment small labeled data set. GPT's spam detection performance can be improved by the constant battle within the text generating and detecting GPT. You can apply what you have learned today. Next week, you should be able to identify a small but very important data within your organization. If you don't have, you can start collecting the data. In the first 3 months, you will be able to fine-tune a pre-trained GPT model to build a classification model to meet your goal. And you can improve the classification model with data augmentation. We introduced this based on the PPLM approach. Within the 6 months, you can monitor the model's performance, and then you can repeat the data augmentation, and you can see the performance improvement. You have learned a very interesting topic here, but also you can learn more from our website, from Sophos AI. We have several research papers related with this one, CatBot, and also we have many different research projects. You can find information from our website. If you have any questions, you can send the question to my email address. Thank you.